Welcome to the lecture. Today I will discuss superposition, the foundation of the ESP, senses, decomposition, how superposition is used, common decomposition techniques, alternative to linearity, and in the end I will tell you the direct method of convolution, that is impulse response. So, how this is the foundation of DSP. The only way of combining the linear system is the sum of scaled versions of inputs. So that thing is superposition. I have explained superposition in detail in the previous lectures. So what is synthesis? If we have impulses and we form a new signal, that is in this form, y of n, we have x1, let's suppose this is x of n. So creating or preparing the signal from components is called synthesis. Decomposition is the inverse process of synthesis. If we have the signal and we decompose it into its components, into its impulses, into its steps, then the process is called decomposition. So let me tell you how superposition is used. Superposition is used to solve complex input signals. Let's suppose we have an example, this one. I say multiply it with the 4 in your mind. What will you do? You will think and you will stop, and it will take a lot of time to calculate this. You will be calculating in your mind, and after some time you will have answer. So if we decompose it into this and multiply each one with 4 and add we can easily get that result. So what is this? This is this sum of scaled versions of inputs. So this is simple, which is superposition. Additivity plus homogeneity. Homogeneity and additivity. So this concept is also applicable for complex signals. So what are common decomposition techniques? The first one is impulse response. Impulse decomposition, sorry. Let we have this signal and we decompose it into impulses. then this process is called impulse decomposition. So what is the advantage of this technique, this decomposition? We can easily examine that how the system responds to the impulses, or we can calculate or we can examine the impulse response of the system by this technique. The other method is Fourier decomposition. Let me explain first the other things, then I will tell you what is Fourier decomposition. Step decomposition. Step decomposition is similar Step decomposition is similar to impulse decomposition. In this, we just decompose the signal into steps, different steps. So what is the advantage of this step decomposition? We can find how the system responds to the step input. When the input signal applied to the system is step, then how it will behave. If we want to find the step response of the system, then this technique is really efficient. The next technique is even odd decomposition. We have the signal. The decomposition of this signal into even and odd symmetry is called even odd decomposition. The formula for even odd symmetries are, for even symmetry we have x of n plus x of n minus, here n is the index around which we want to find the symmetry. In the previous example that I have drawn the signal like this one, I have taken 0 as n. So this was the formula for even symmetry, and for odd symmetry the formula is similar, but the only difference is this minus sign. So if we want to check whether the signal is even or odd, we can use these formulas and check it. The next, so what is the advantage of this technique? This technique is used to tell us the circular symmetry, because the start and end of the signal is not very common. So this is also used in Fourier analysis. The next one is interlaced decomposition. We have signal x of n is equal to in this technique, the signal is decomposed into even odd indexes. For even we will have 0, then on 1 it's just like this one. For odd we will have 0, 1, 0, -4, 0 and 3. So this is interlaced decomposition. So what is the advantage or importance of this interlaced decomposition? This interlaced decomposition is used on the basis of fast Fourier transform. Fourier transform is the mathematical technique to or algorithm designed in 1960. So modern computers take so much time. Performing Fourier analysis or Fourier transform on modern computers will take a lot of time. To reduce that time or to minimize and do the processing quickly, we use fast Fourier transform. Fast Fourier transform is introduced after 1960 and Fourier analysis was before 1960. So the last technique of decomposition is Fourier decomposition. The decomposition of input signal into sinusoidal waves or sinusoids is called Fourier decomposition. So what are the advantages of Fourier decomposition? There are three main important advantages of Fourier decomposition. The first one is complex signals or input signals are easily decomposed into sinusoidal waves, and those waves are easily processed and analyzed, and the output is all easily calculated. The second advantage is linear system behave similarly or in a unique way to the sinusoidal signals. As I have explained in the previous lecture, sinusoidal fidelity. Linear systems always have sinusoidal fidelity. The third and important advantage of Fourier decomposition is Fourier analysis, the mathematical technique or procedure to solve problems, and more advanced mathematical techniques that are Z transform, Laplace transform, etc. These are more advanced mathematical techniques. We will study Z transform in upcoming lectures. So these were the common decomposition techniques. So what can be the alternative to linearity? If we have non-linear signal, what we will do? There are three ways. First, if there is very little non-linearity, just ignore that linearity. The second thing, keep the signal very small. And the third approach is logarithmic approach. Let two signals x sub n are multiplied and if we take log of this, it will become like this one. As you know, the property of logarithm is multiplication is converted into addition. Now you can see that the signal will behave linearly and you can calculate the linear response or linearity. This is alternative to linearity. So this was the end of chapter 5 of the book named Engineers, Scientist and Engineer's Guide to Digital Signal Processing. Now we will start chapter 6 of this book, that is convolution. First of all, there are two ways. The first one is direct method. Today we will discuss only direct method, and in the next lecture we will proceed further. So let's suppose we have input signal system. Sorry, we have this system. And we want to find the impulse response of this system. So what is impulse response? As I have explained in the previous lectures, let me just revise you. Impulse response is the response of the system to impulse input. When we feed the system with impulse, and the response that system produces is called impulse response. And that is denoted by H of n. So now we want to find this H of n. Start with -1. What will be the output? Delta -1, 0. Delta -2, 0. As we know that delta is equal to 1 when n is equal to 0 and 0 otherwise. So what is n in this case? -1. So this one 0, this one also 0, this one also 0. So first thing is this is 0. Now H of 0, this becomes delta of 0, which is 1, and delta of -1, 0, delta of -2, 0, this becomes 1. The next thing, H of 1, put this one in this equation, delta of 1, 0, delta of -2. What will be the result of this one? Delta of -2. -2 into delta of 1 minus 1, delta of 0, 1, plus delta of -1, already 0. So this becomes -2. The next one, H of 2, is equal to delta of 2, 0, delta of 1, 0, plus delta of 0. 2 minus 2 is equal to 0, delta of 0, 1, this becomes 3. So if we move further, delta of 3, h of 3, 0, 0, 0, 0, and so on. So what is the impulse response? H of n will be 0, 1, minus 2, 3, 0. This is 0 index at one magnitude. So there is a direct approach that you can see, you can get this result by looking at this one. You don't need to follow this whole procedure, just look at this. The result will be at 1, 2 and 0. So what are the magnitudes? At 0 magnitude is 1, at 1 magnitude is 2, at 2 magnitude is 3. So you can see that we can directly calculate the impulse response of this system. That's it for today. If you have any question, ask me in the comment box. Thank you very much, and we will continue in the next lecture. Thanks.